Swayam Prabha. Digital India. Educated India.
Welcome to lecture 5 of mechanics of materials. In the last lecture we saw what displacement field is, how to represent a displacement field using material representation or spatial representation, and then what a motion field is and what a deformation field is. We also saw what traction is. We defined the traction as the distributed force acting over a cut surface or boundary of the body. This is where we stopped in the last class. Today we will continue to see what this traction depends upon and how the dependence on various variables are. We will denote the traction as denoted by T's of n, and this is a vector function of time. You can understand that it will be a function of time because the forces can vary with time, and hence the distributed force acting over a cut surface also can vary with time. In general, it will depend upon the position vector of the particle, position vector of the particle which you are looking at, and it depends upon the normal to the cut surface also. Okay. If I take a bar with the force P applied, which is a function of time, you understand that the traction, which is the force acting over a cut surface like this, will also vary with time. If I take a bar and subject to a bending moment, the stresses cannot be uniform because it should produce a moment about the centroidal axis x and y, and hence the stress distribution will be something like this, non-uniform stress distribution, which means it will depend upon the location, whether you are looking at this point or this point. The traction will vary depending upon the location of the point at which you are looking to find the traction. This dependence on the normal is something you have to understand. How does it depend? Okay. Now let us take this example of a uniaxial bar, a bar subjected to a uniaxial state of stress, which is this, and say I cut this body into two different cuts, one vertical and one with an inclined cut at an angle of theta with the horizontal. Let us see what is the traction at this point, at this intersection point. At this intersection point I want to find the traction. Okay. So let us proceed. Let me assume that this force is uniformly distributed. So if I cut it like this, in this cut there will be a uniform distribution of stress or force, same here there will be same uniform distribution, such that these two add up, this will have the same magnitude, these stresses will have the same magnitude, but they are opposite in direction. One is like this, the other one is like this. So when I apply a P, the sum should total to P, and hence the sigma would be, if that is sigma, that will be P by A, or traction. If I take x and y as this axis, let me take x and y as this axis, traction T's of Ex would be P by A times Cx. Okay. Now let us do what happens with the red cut. With the red cut, I have same P acting here and here. I have this inclined surface, the same inclined surface here. Okay. Now there is going to be two components of stresses, one which is a normal component of this traction, some traction acting like this, and some other traction acting like this along and perpendicular to the plane. Same way here there will be this traction acting opposite to that, and this traction acting opposite to this. Right. Okay. Now let us find what those tractions are in terms of x and y coordinate system itself. In terms of x and y coordinate system, I want to find what is the traction T's of, let us say this one is n, T's of n, I want to find T's of n. Okay. Now what happens is I have to resolve this force along n and parallel to the plane and perpendicular to the plane of cut. Now I have to resolve this force parallel to the plane of cut and perpendicular to the plane of cut. This P, we said that this makes an angle theta here, this angle is theta, so this angle would be theta. So this component of this force would be P sin theta, and this component of the force would be P cos theta. Right. Okay. What I have done is I have resolved the force normal to the plane along the n direction and parallel to the plane, this is along the n direction. Okay. Now what happens, now if I assume that this P cos theta and this P sin theta is distributed uniformly over this inclined surface, then what will it be? Let me assume that it has a square cross section. Let me assume the cross section is a square and this dimension is d, the cross section is square, so I will have in y and z I will have this is d and this is also d. Okay. So area here would be P by d square Ex. Okay. Now what is this inclined area? This inclined area would be that wherein this width would be d and this makes an angle theta, this is d, hence this distance would be d by sin theta. Okay, that it will be d by sin theta, right. Okay. Now what is this traction T's of n then? T's of n is this P cos theta distributed over P cos theta distributed over this area, which will be d into d by sin theta Ex plus P sin theta, which is this, it is not Ex, it will be along this direction, say this direction was m, this will be m plus P sin theta divided by d into d by sin theta into n, because that is acting along the n direction. Okay. Now let us simplify this further. We got T's of n as P by d square, going back to this equation is P of d square cos theta sin theta m sin square theta n, right. So it is P by d square cos theta sin theta m plus P by d square sin square theta n. Okay. Now I want to convert this back into Ex, Ey, Ez coordinate system. So what is Ex in terms of n and m? Ex is this direction. How can I write Ex in terms of m and m? If this is theta, Ex would be cos theta into m plus sin theta into n. Okay, that is theta. So Ex is cos theta m plus sin theta n, resolving this along m and n direction, resolving Ex direction along m and n direction. So coming back to this, we saw that Ex is cos theta m plus sin theta n. So I will rewrite this equation as P by d square sin theta into cos theta m plus sin theta n, which is nothing but P by d square sin theta into E of x. This is the traction along the normal direction, where n is, if I resolve n, it will be, what is n? If this is Ex, Ey, this is n, this is m, this angle is theta, this angle would be theta, n would be sin theta Ex plus cos theta Ey. Okay. So that is n. So to write it more specifically, T sin theta Ex plus cos theta Ey is P by d square sin theta Ex. This is not equal to T's of Ex. Okay. Thus we find that the traction T's of n is a function of the time, the position vector of the particle that you are considering, and the normal to the cut surface that passes over that point. That is, if I have a body, it depends upon, and say I have a coordinate system Ex, Ey, Ez, and I have this point in the body whose position vector is x. It depends upon that, and not only that, it depends upon how you cut the body also, whether I cut it like this or whether I cut it like this. At the same point, the traction will depend upon what is the orientation of the cut plane, and at the same point the orientation of the cut plane determines what the traction at that point is. Okay. Traction in the sense of is a distributed force acting at that point. Okay. The traction depends upon not only the time and x, but also the orientation of the plane at which the cut is made. Now next what we want to do is, we want to understand how this function will depend upon n. For this we appeal to Newton's third law. Third law, we know that if I have a body I have been using this all along in our discussion. If I cut it like this, what happens? The traction acting on this cut surface on the opposite sides of the body on this cut surface, this is the distributed traction acting on this cut surface. This is say T of n. N is normal to this cut plane, that is n, and normal to this cut plane is say n star. Okay. The traction acting on n star would be like this. This traction is T of n star. What do you know between n and n star? N star would be minus n, right, because these are outward normals, one is pointing like this, the other normal would be pointing outwards in the opposite direction, but they are unit vectors, so the direction would be like this. Okay. Now what can I say about T's of n and T's of n star? According to Newton's third law, T's of n plus T's of n star has to be equal to 0. In other words, T's of n plus T's of minus n has to be equal to 0 vector. What does this mean in terms of the function? This means f of t comma x comma n plus f of t comma x minus n has to be equal to 0. Okay.